All right, the rest of the mechanics questions then from the year two book. Let's just get straight into it. This one's kind of interesting. What I chose to do was continue this A line out like this, and then clearly this angle here is 180 miles beta. And then what you can do is you can kind of copy this C force and put it up here, which of course makes this angle also 180 miles beta because it's corresponding angles. And then kind of just do the same going around. So put this B1 up here, but then you can argue, so this is now the new force B. But then you can argue, of course, drawing a line out here that, of course, this angle is 180 minus alpha because that's the 180 there and that's the alpha. So that can get put, I guess, up here. Again, corresponding angles. And then this one is 180 minus gamma. Put it up there. And now we've just made a triangle with A over sine this, B over sine that, C over sine that. Of course, all works just by sine rule. And now we just need to show that these things are just equal to those things. You can use graph transformations or you can use just this. And it just works out very well. So you end up with what they're asking you to get. Kind of interesting. For this next question then, we obviously need to put in the forces. So obviously mg comes down, or m1g, I guess, which means this is mg or m1g sine 30 coming down here. And then this is mg, sorry, m2g cos 60, because of course this angle is 60 because of triangle stuff. So okay, that's cool. If this is smooth, that's all that's going on, right? And if they're in equilibrium, then of course this force is equal to this force because neither of them is moving. We can just cancel the g's, put in the things that we know, and then we end up with this very quickly. Now we know that apparently it's not smooth, it's rough. So now we need to introduce some forces going backwards for resistance or friction. Now, of course, the force coming out here is m2g cos 60, right? And then here m1g cos 30. And so you times that by mu to go backwards. The thing is, though, either this is trying to pull this way, in which case this friction is going up and this friction is going down. Because, of course, if this is trying to pull this way, then this one's trying to go up, which means friction is acting opposite, going down. And this could be the picture. And now we can say, okay, well, we need all the forces pulling downwards, or we can say maybe anti-clockwise, to be equal to the forces turning clockwise, which we can say is this one just on its own here. And if we deal with that, we end up with this, and then just working out all the stuff, putting it in here, rearranging for M2s and M1s, and then we can solve like this. And that's the case if it's trying to pull downwards. Of course, you can then go all the way to the other case where this one is trying to pull downwards, where this friction swaps over, and so does that one. And we end up with a thing that looks more like this. Again, this one is now the only one pulling on its own. Put all the stuff in, rearrange for M2s and M1s, and you end up with this. And so therefore, M1 and M2, or M1 over M2, is between. Notice how the first thing was just this one here. Sorry, it's this one. Which one is that? It's this one here. And then the second thing is this one here. So therefore, the two values of the division is in between the two of them, because it's somewhere in between the case of it pulling this way and the case of it pulling this way, because of course it's an equilibrium. Okay, so this question is kind of weird. We have something passing a control tower with this velocity. Now I'm going to call the control tower the point 0, 0. So if you imagine an XY axis, just going to define the control tower to be the origin. I'm also going to say time is 0 when this happens, when it passes at this velocity. Now it has acceleration 6j, so I'm going to integrate that to say the velocity of the first plane, which I'm going to say is v1 for the first aeroplane. Just integrate the i's and the j's separately, so the 0i integrates to ci, and then this integrates to 6t plus dj, j, yeah. And then you know that it's going through at this velocity when t is 0, so that immediately gives you those two figures there. So we have this for v1. Then we think about the second plane, which has acceleration this. So again, just integrate it. I should have called these different to c and d because I used them there, but I guess we actually know those values, so I guess I can just use them again. But they don't refer to these two things. But whatever. So integrate this, you get this. Now I know it goes at this speed, but I only know that it does that at time t. So basically, I mean, I know c is 70 because that doesn't depend on t. And I know this thing here is 40 when t is t. So I'll just write that there. Next, the only thing that I know now is that the two airplanes pass directly over one another again. So that means their I coordinate and their j coordinate is equal for some other value of t. They're directly in the same place at some other later value of t. So well, I need the positions then. So I need to integrate both of these things again. So integrate this, get yourself a new couple of constants. And then, of course, we can say here, we can get rid of alpha and beta because we know at time 0, as I said before, I defined the control tower to be at 0, 0. So at time 0, both of these things should be 0. The position should be at 0. So alpha and beta are both 0. So we end up with this. For the second plane, we integrate this, of course. And this is 70i, and then this. So we integrate that, and we get these things here, just made some new constants. And now I don't know anything about that. I know that when t is t, I know that that's at 0, 0. So when t is little t, I know that this is at 0, 0, which I think I'm about to say in a second. Yeah, I'll say that in a second. Yeah. Anyway, from here, I'm going to define big T to be when they collide. So I'll say that 20 big T must equal this for that big value of T. So a later value of T when they collide. And also this must equal this for some other big value of T. And now I'll say when time is T, the position is 0. So I know this when time is little t is 0, and this when time is little t is also 0. It's kind of confusing that it's actually their fault that they've used T to denote the amount of time when I'm also using T, obviously, to denote the variable time. So this is no longer a variable anymore. This is just a fixed time T that I'm going to try to solve for. I actually don't need any more variables at all. We're just going to focus on this, and this equations. So, okay, what can we do here? Well, we can do this equation, take away this equation, which will give us this. And we can do this equation, take away this equation. And that gets rid of the gammas and the epsilons, which is super helpful. And now if I rearrange this for big T, like this, I can just throw that big T straight into here. I've also thrown this value of D is 40 plus 8t, into here as well. So here I've got big T, little t, and D. I can get rid of all those variables except for little t by putting in this value for big T and 40 plus 8t is D. And I can put all those in. I'll end up with just an equation of T, which is good because I'm trying to solve for D. So I'll just expand all that out, collect some stuff together, and I'll solve it, divide by T because apparently T is 0 as a fake solution, and we'll end up with this value of T. Kind of a difficult question, but also quite interesting. Much easier questions coming up here. We're just going to integrate this, of course, are we? Yeah, because we want S. So we're just going to integrate this separately. This is a little bit of integration by parts. Integrate cos for sine, and then take away the integral of this differentiated as 1, and then that still integrated as sine. That's super easy to integrate. Don't forget your plus c's, which I think I added because I just did it with this integral instead. So that's all fine. And now it just says when t is 0, we are initially at the position 0. So we know that when t is 0, this whole thing is, we're at the position vector 4i plus j. So this whole thing is 4 when t is 0. And when t is 0, of course, that goes away, and that turns into a 1. So we get this. So c is 1. And we know that this is 1. T is 0 makes this go away, so d is 1. Good. So we end up with this here. And now we just need to put in pi over 2. And we'll get to this answer here. When we multiply that out, we'll get that thing there, and we'll be done with that question. Next question, then, we have displacement given like this. State the initial displacement. So we just put t as 0 in, obviously, and it just becomes 20. Changes direction. So if it changes direction, so it's just moving along the x-axis. So follow the mouse. If it's going this way and then changes direction, there's a moment where the velocity has to be 0, right? It's got positive velocity here. If it changes direction, there's a moment over there where the velocity is 0. So the velocity is, of course, ds by dt. So we just differentiate. I've just done product rule here. So here is just this one differentiated, and then here is this one differentiated, and the other two left alone. Set that to 0. So that's me setting the velocity to 0. That's going to see when it changes direction. Times everything by t plus 1 to the power half to get rid of these square root things. And then you can just solve this, right? Double everything, solve it, super easy. Get t as this. We obviously want the positive one, so t is that. So that's the time in which it changes direction. And it only changes direction once because the other time it changes direction is when t is negative, so that doesn't count. Find the exact speed when it crosses 0. So like I said, the velocity is this thing here. When it crosses 0, its displacement is 0. So we just set this into 0, and we solve for the time in which that happens. Obviously, this is not going to be 0, so we need t to be root 20. So we're then just going to put root 20 into here, and we're just going to type it all in, and we get v as this, and that will be the answer. Next one is going to be just finding our dot. Our dot is dr by dt, so we're just differentiating this. The omega comes out, sine turns into a cos, this turns into minus sine, should just be this. And hence show v squared equals this. So, okay, well, dr by dt is v, right? It's the velocity. And this v refers to the speed. So we just need to work out just doing Pythagoras, just root of this squared plus this squared, the magnitude of the velocity. So yeah, let's do that. Let's square them out. We get this. Now, sine squared plus cos squared is 1, which would be very helpful if these things match. So why don't we just force them to match by writing 20 of them plus 16 of them. This, therefore, factorizes out, bring out the... oh, I squared both sides as well, because they will actually want v squared, right? Anyway, bring out the cos squared plus sine squared. That becomes a 1. And you end up with this, which I think is basically what we were being asked for. And then we just need to turn this into a 2 omega t. So we just need to use this formula, change it into just the cos one, and then rearrange for cos squared, and you end up with this here. And then we can throw that result into there, times it by 20, just turns everything into tens, I guess. And then we can finally bring it together, factorize out all the stuff that we need to, and it turns out to be perfect. So that's fantastic. Deduce this thing here. Now, this is the reason they've put it in this form here, because the largest cos of something can never be as 1. So the absolute largest this could be is 13 plus 5 times 1, which is 18, times 2 is 36 omega squared. And then if we root everything, we'll get v is 6 omega. So that's the upper bound. And then the least cos can ever be is minus 1, so you turn this into a minus 5. That makes that an 8, which times by 2 is a 16. And then we root that, and we find the minimum of v is 4 omega, which is this bit here. At the instant when t is that, find the angle between r and r dot. So okay, well, r is just this thing here. If you put in t as pi over 3 omega, because the omegas cancel, sine of pi over 3 is root 3 over 2. So you get this, and likewise for the cos. You can also put this, of course, into dr by dt, which is r dot. And something very similar will happen. And now we just need to find the angle between this and that. Now, there's a few ways you could go about doing this, but what I noticed is that this one, of course, goes across this far, up this far, so that's r. And this one goes across some other distance, and then downwards instead, like this, because of the negative. So you can just do a bit of inverse tan to find this length, sorry, this angle, and then you can do inverse tan because the omegas cancel to find this angle, and then you can just add the two together to get your answer, because you can almost place the triangles together, r like this, r dot like that, and the angle between them is just the sum of those two things there. Final few questions to do here then. So got a lot to fill in here. 0.5k is there. The whole thing is 2k, which means this is 1.5k. The thing is uniform, so 1k along is going to be where the weight is at, which is 100. And then this height is 0.3. What we'll do is we'll work out this theta very quickly. It's sine inverse of 0.3k over 0.5k, except I don't need to do that really, because what I can do instead is just do a bit of Pythagoras and work out this length is 0.4k. It's a 3, 4, 5 triangle, which means sine of theta is just 0.3 over 0.5, which is 3/5, and cos of theta is 0.4k over 0.5k, which is 4/5. And that's going to be super useful because I'm going to want to turn all of these forces into coses, because they'll be adjacent to the angle, right? So that's going to be an f cos theta, which is 4/5 f. That's going to be 100 times cos theta, which is 4/5 times 100, which is 80. And this one is going to be mg times cos theta, which is just 4/5 mg. And now just take moments from here. 0.5k times 4/5 mg needs to be, if this force is indeed bringing it down, needs to be less than 0.5k times 80 plus 1.5k times 4/5 f. We just sort that out, and it turns out to be the thing that we want quite quickly, which is good. Next then, we have velocity is this, and we know the acceleration is 1.5 when t is 0. So let's differentiate this first. To find this, k of course comes out the front, sine differentiates cos, cos to minus sine. Set that when t is 0 to be equal to 1.5, and of course the sine will go away, the cos will become a 1, so you just get 3k as 1.5. So k as a half, so let's write this out again with k as a half. And now maximum distance, just like we saw in the previous question a couple of times ago, max distance away is going to happen when v is 0 momentarily, because then it's going to be turning around again. So let's just set v to be 0. And we'll get this. Solve that by taking the cos over, then dividing by cos to get tan. It will end up being this. If you do tan inverse this, you'll end up with like minus something. Just add 180 and then double it, and that will be the first time in which v is 0, and it ends up being this. So that was just tan inverse, add 180, and then double it. And now, of course, we can start thinking about the actual s, because we want to know the max distance. So let's integrate this here. We get this, plus c, of course. We can work out this c because we know at time 0, we're at 0. So let's put in t as 0 and s is 0. T is 0, of course, makes this go away, makes this a 1, so that becomes a minus 6. So c is going to have to be 6 to balance that out. So we have s as this. And then, of course, we just put in this t, value into this s, and if you just type it in, you get something around there. The very last question then, very similar to something we did in the previous video. What I'm going to say is this curve here, the arc of the thing being projected, is given by this formula. And I'm just going to put an x-y-axis over the top and define the starting point as 0, 0. Now, this angle of projection, if we do some angle chasing, alpha there, sorry, theta there because of alternate angles, and therefore this is 90 minus theta. So that's all that in there, with u, of course, being the initial velocity. Now, this line here, it's got gradient this over this, right? So it's just y equals minus this over this x. But this over this is also tan theta, right? Tan theta is opposite over adjacent. So the equation of this line is just y equals minus x tan theta. And I'm going to look for the intersection between this curve, the red curve, which is this, and this line. So just put that in there. And now I'm going to need to deal with this for a second. So tan of 90 minus theta, you can use sine over cos for this, and then do the compound integrals on sine and cos, and then a bunch of stuff cancels down to this, which is just cot. So that's super helpful. So let's replace these two values with cot and cot squared. Now let's do some solving. Or 1 plus cot squared is cosec squared. That's quite useful. Now we can maybe do some more stuff. So divide everything by x, because x equals 0 is a solution that I know of and I don't care about. So now finally rearrange for x, and you end up with this. Except I'm just going to do some work to this first, because it's going to be annoying if I leave it like that. Cot is cos over sine, this is sine over cos, and this is 1 over sine squared. So I'm just going to write it like this. Add these together to get cos squared plus sine squared over sine cos, which is 1 over sine cos. 1 over sine cos squared dividing by is the same as timesing by sine squared. Cancel this down, and you just end up with sine over cos, which is tan. So that's the x coordinate. And now I can just find the y coordinate by shoving the x coordinate into here. So it's minus tan lots of this, which is just this. And now that what I'm saying here is it goes across this far as the x, and then this far as the y. And to find the distance, I'm just going to do this squared plus this squared square rooted, which ends up being quite nice. You can factorize out the 2u squared over g tan, because all of those things are being squared anyway. So just factorize them out and then take them right out, because they're being squared and then square rooted anyway. Leave behind nothing in here. I've taken out everything, so it's just 1 squared plus. And there's only one tan left in here. So 1 squared plus tan squared is, of course, sec squared, and then root of sec squared is just sec, and we get what was required. Thanks for watching.